So in this final segment, we're going to talk about trial and error learning or exploitation versus exploration, right? The whole idea is that when we talked about in the last section, the reinforcement learning problem as being an agent dumped into an unfamiliar environment and needing to struggle to figure out what actions that it can take and what rewards it's going to get after taking certain actions is to basically try to discover what is a good policy and do so by trial and error, by playing on the environment and experiencing what types of observations and reward it gets for doing certain actions, right? But we want to do this in such a way that it doesn't lose too much reward on the way. Right. So, for example, in our decision tree learning case, we had this idea of trying out new restaurants, right? Or a restaurant selection, I should say. So we could decide to go to different types of restaurants, either ones that were where there's no patrons, some patrons are the restaurant is full and we have to wait, or going to a restaurant dependent on the type of cuisine it has, right? So, we might have a certain, through the reinforcement learning process, we might have discovered certain restaurants that we like and that we want to keep on going to generate good rewards. But on the way, we might find out that, experiencing the environment, we might find that there are other restaurants that are worthwhile trying out, and in that way generate an additional reward. So this is the basic difference and paradigm that we need to explore, thinking about these two different types of behavior, right? When we are exploring, we're basically saying at the beginning of the reinforcement learning algorithm, I have no data, so I have no choice. I will be doing some exploration, right? So I want to discover more about the information that's encoded by the environment and how it reacts to the types of actions that I perform. Right. So after doing this for a little while, maybe there are going to be certain actions that are more rewarding than others. So I will tend to want to exploit that information. Like, for example, I just came to an unfamiliar city for the next couple of days for a conference or for some work. I quite liked the meal that I had last night, so I'm going to continue going back to that restaurant to maximize my pleasure from dining there, right? So after a while, I might find out actually that I need to alternate, doing both of these. For example, I might get tired of going to the same restaurant, having the same dishes, and I might get tired of, taking the same courses and want to try something different. So it's usually quite important to explore and exploit, and then have these two cycles used interchangeably in different times in our time step. But as we said on the last slide, it's important to do this without losing too much reward along the way. Because if we lose too much reward, then we've obviously done something wrong. We could have had a more optimal method for exploring the state space. Okay, so we're going to end with one paradigm difference between the idea of prediction and control. So these are two correlated problems that we have in reinforcement learning as well as in control in general. So the idea is that, if I'm given a certain policy, like I am told how to behave given certain states, can I predict how well I will do in the future, right? So basically, given a particular policy pie, tell me what type of rewards that I'm going to get at any type of future type step T, okay? So that's the prediction problem, right? And once I have a prediction, so I can then stick in any policy here, right? I can evaluate how good it is, evaluate the future fitness of that particular policy. Then this prediction problem facilitates me to do control, right? To say, okay, well, I've got a whole bunch of different ways that I can behave. Those are all different policies. So I want to optimize for my future rewards. I'm going to find the best policy out of everything. So let's take a look at this in the context of our grid world, okay? So here's an example of a 5x5 grid world, right? And, you know, we might say every time we take a particular action to go up, down, to the left or the right with any time step, I'm going to lose 1 point, okay? Because I have to consume some fuel and some time. Okay, but interestingly enough, you know, in this grid world, there are certain things that might give us a reward. So, for example, let's say you reach coordinate A or coordinate B, suddenly, for whatever reason, you get some positive value in your reward. So, you reach this peak of the mountain in this space, and you're able to see out on the vantage point, and you feel good about that. So, you get a +10 or a +5. But right after doing so, then you're teleported automatically to a new place. So you move back down the mountain, for example, and you can start again. Okay, so in this type of environment, where I have, let's say, a uniform random policy, so that means for any particular location, all of these particular actions are exactly 1/4 possible. Okay, where of course at the side I only have two places where I can go. Sorry, at the corners, right? So if I have a random policy that's uniform, then I can use that to predict what's my value, right? So of course, if I'm at this location here, I'm going to get a +10, and then that's reflected on my utility or my reward value here, and I get teleported down to the next place for the next action, right? So if I run this simulation over this particular uniform random policy, I'm going to be able to estimate what my rewards in the future are going to be. Now, contrast that with prediction, right? Contrast that with control. Control is the case where we're looking for the optimal policy or optimal value function over all of the different policies that we have. So you want to engineer what's the correct decision given any state that I'm in, okay, for the rewards that I might observe, right? So in this case, of course, the numbers that we would get in our value function are going to be much higher in the last case because it's basically optimal, right? So if I always take the optimal action, I can expect a higher reward for being in certain states, right? So then I can engineer the best possible policy here, the stars standing for optimal, right? So we can see that the best thing for me to do is just continuously go up and up and up because I spend 5 time steps, incur a cost of 4 to go up and get my +10 reward, and I'm going to start back down at the bottom of the mountain here. Okay, so that's the whole idea behind the relationship between prediction and control, where we'll say that prediction facilitates control because prediction allows us to evaluate how good a policy is for the state space.